Good afternoon. My name is Vince Coonce, and I'm here to talk about engineering considerations in traditional kiln design and specialty malt formulation. To start, I'd like to let you all know that this is not a research paper. There is no new information presented. There is no new data presented. If anything is new, it's simply a data format, data presentation format. For that reason, I thought it would be best to just leave this as an informal type presentation. And being informal, it was okay for me to shamelessly steal slides off the internet. And so that's what I did. I shamelessly stole slides off the internet. Now, shameless really does mean no apologies, but it doesn't stop me from thanking those who built the slides that I shamelessly stole. So thank you. So today, a colleague of mine told me that you would like to hear about physical specifications in kiln design and specialty malt recipes. Physical specifications like flow rates, like temperatures, like times. And I was thinking it would be really easy for me just to pull out the Anheuser-Busch specification sheet or the Heineken specification sheet and show you all the different numbers that kiln designs are already spec'd at. But I then thought it would be much more powerful if I showed you the theory, the principles, the engineering calculations that are used in creating those specifications. So instead of giving you a list of specifications, I thought it better to show you how to create your own specifications. And in doing so, you would have a much greater understanding of the kilning process. So today we'll talk a little bit about some traditional kiln design. Traditional being a very difficult word for me in kiln design, as there's a lot of different kilns and no two kilns are exactly alike. Basic air handling operations in kilning. I'll take a kiln design and I'll split it into a series of air handling unit operations. And then we'll go into malt drying theory. We'll talk about how malt is a hygroscopic product and how that means that it is in equilibrium. It's in moisture equilibrium with its environment, and that its drying characteristics change as the environment changes. And knowing that it's hygroscopic, that malt is hygroscopic and is in moisture equilibrium with the environment, we will go into psychrometry, which is basically a way to completely define all of the physical properties of air and water mixtures. Psychrometric charts, and what my go-to is not psychrometric charts, but actually online psychrometric calculators, electronic psychrometric calculators. And then we'll go into some kiln operations. After that, after we're thoroughly confused on malt drying theory, we'll start talking about specialty malts and what makes specialty malts different from each other, what distinguishes one malt from another malt. We'll talk about color and flavor formation mechanisms, and that would be useful for producing specialty malts with color and flavor. And finally, and only because I ran out of time, we'll talk about some specialty malt recipe development, some colored malts. I'll just introduce caramel malts because I don't have the time to go into that. You can produce caramel malts on kiln. And then finally, another specialty that you produce on kiln in a totally different way from colored malts is high enzyme malts. And if there's anybody who has a specific malt that they'd like to talk about, ask me a question later, okay? That works for me. So the traditional kiln. Now this is a traditional single deck kiln. For me, Traditional didn't start out being a single deck kiln. My first kiln was a double deck kiln and a triple deck kiln, and I had 6 of them, 3 of each. I didn't even see a single deck kiln until I went to Europe. But anyway, this is a traditional single deck kiln. If you can follow the airflow, you've got outside air that comes in and runs first through what we would call an economizer. And that is simply something that preheats the air using the waste heat from the exhaust that's going out the door. Okay, that air runs through heating coils to get to a set point. You know, for base malt, you would be using somewhere between 125 and 160 degrees Fahrenheit, depending on what you're, you know, what you were doing for holding heats, what kind of malt you were making. This is actually a circular kiln, so the grain bed is on the floor. The hot air passes through the grain bed and picks up moisture, which is the whole reason for the kiln, is to remove the moisture and later on to add flavor and color during curing. The exhaust air off the bed then can be recycled back into the heating coils. So what that would do is it would be recycled and added back to fresh air inlet into the heating coils. If you're lucky enough to have a kiln that has recycle, then you will be able to make a lot of different types of specialty malts. Recycle on a single deck kiln does just about the same function as what you can do on an upper deck of a 2-floor kiln in specialty malt design. All right, and you have a fan that pushes all the air, right? Constant volume. So that's a basic traditional kiln. This is a picture of a circular single deck kiln. Really good features for kilns today. Wasn't available 35, 40 years ago, but today, variable frequency drive fan speed control. So you can lower your fan speed down to roughly, you know, at best 40% of your maximum capacity. I'm showing you a specific airflow capacity here, 55 CFM per bushel. That comes right out of Anheuser-Busch. In tons, that's a 2,300 CFM per ton capacity. That comes right out of Anheuser-Busch, and I like that as a capacity minimum because with that capacity, you can achieve less than a 24-hour cycle. So what that means is if you're running full tilt and you're producing a 24-hour kiln every day, 55 CFM per bushel will get your kiln dry and allow you time for emptying and refilling within 24 hours. You can go higher than that, and just be aware when you go higher than that you're going to probably run into issues with channeling, which is where one part of the bed will dry out and all the air will run through that part of the bed without drying the other parts of the bed, or you will run into problems with blowouts, which is where part of the bed just kind of explodes, and then you have to shut down and fill that hole back up again. And of course, you can control the blowouts and measure whether or not you're bypassing, using static pressure measurements, which is very simple. The other thing this has got is the recycle capability. So bringing, as we'll see later, bringing high energy, high humidity air back into the burner to raise, and what that'll do, as we'll see later, is that'll raise the effective temperature of your bed. Using recycle will raise the effective temperature that the grain sees in your bed. This is a picture of a double deck kiln. This is actually a Briess kiln, Kiln 5 at Briess. So a double deck kiln is, if you haven't seen one, is basically you load. This is the upper floor. You load the upper floor with wet malt. Um, and then you, after the lower floor is finished, you dump the lower floor off, and then you dump the upper floor to the lower floor, and then you load the upper floor again. So you basically have super wet malt on the upper floor, and you have half dried malt essentially on the lower floor. These are very efficient if managed properly, because you can effectively utilize 100% of the drying capacity of your air with this setup. You can do the same thing with exhaust recycle, and this double deck kiln actually has exhaust recycle as well. Then there's something called bypasses in a double deck and a triple deck kiln, and that's where some of the air doesn't go through the lower deck, but gets bypassed around the lower deck and gets fed into the exhaust off the lower deck to feed the upper deck. And this kiln actually has heated and cooled lower floor bypasses. So there's a lot of things you can do with these kilns, you know. But if you don't know what you're doing, you know, you can make a big mess with all this control capability. So for the single deck kiln, this is my my drawing of the different air handling unit operations. So we'll just go through this again. It's identical to what I showed you before, just in a different format. Fresh air comes in through the economizer. It gets preheated. It meets up with some recycled air, right? And at different conditions, water can fall out of air at that time, and so water has to leave that. Will have to leave that blending operation. That blend of recycled and preheated fresh air gets fed into the heater, where we add energy to heat up the air to a set point. From that, we go through kiln fans to increase the static pressure, and then that goes through a malt bed where we have adiabatic saturation occurring at the early stages of kilning. And then we can split off for recycle or exhaust, and the exhaust will go through the economizer, and that's what preheats the fresh air. All right. So these are all single unit operations. These are all single air handling unit operations. This is a heating operation. Well, actually a heating and a cooling operation simultaneously. We have a blending operation. We have a pure heating operation. We have a pressure improving operation, and we have you know, the malt bed. So we have all these unit operations all dried out. So malt is a hygroscopic solid. What that means, the important part of what that means, is that malt is in moisture equilibrium with its environment. That's all there is to it. What that means is that different environmental conditions will cause the malt moisture content to change differently. That's how simple that is. The thing about hygroscopic solids is they have characteristic rate of drying curves. So this is a characteristic rate of drying curve. On the y-axis, you have what's called the normalized drying rate, and on the x-axis, you have the dry basis moisture content. So on the x-axis, moisture content's increasing, okay? So if I'm drying, then I'm always moving from the right to the left. The right to the left. So I'd be starting out here somewhere and drying along in the free moisture until I hit the critical moisture content, at which point now my drying rate starts to fall. That's it. That's how hygroscopic solids dry. You can actually build, if you have exhaust temperature history from a kiln, you can actually draw this right off that exhaust temperature history and use of a psychrometric chart. Or on the other hand, if you have this drawn already for your product, then you can build the exhaust temperature history that you're going to see when you turn the kiln on. So these different drying zones, to me, it's a lot easier if I kind of like visualize, why these zones are there. If you can visualize that early on when the moisture content of your malt's super high, that you've got moisture just hanging around, not really locked up in anything, basically free, unbound moisture, that will evaporate readily. Okay. But as that disappears, then you start hitting to the bound moisture, and in this point, water actually has to migrate from the inside to the surface of what it's bound into, and that takes time. So bound moisture takes longer time to remove than free moisture, and that's why the rated drying curve for hygroscopic solids looks like it does. And since hygroscopic solids are in equilibrium, moisture equilibrium with their environment, and the drying of hygroscopic solids is dependent on the quality of the environment, then we need psychrometrics then to talk about the humidity in the environment. So basically the air and its moisture handling capabilities. Okay. So here's just a couple of definitions I pulled off the internet. Psychrometrics uses thermodynamic properties to analyze conditions and processes involving moist air. Almost the same definition, but this goes more into thermodynamic properties of air-vapor mixtures. And it specifies temperature, partial pressures, and enthalpy. Enthalpy being energy. We're going to go into all this here pretty quick, all right? Psychrometrics for me, this is my important thing. I can use psychrometrics to define processing methods to achieve and control different combinations of grain, moisture, and temperature. And hopefully what I convey in this talk is that if we're looking for color and flavor development, the grain temperature is the most important, is the important value. The grain temperature is what the chemical reactions the chemical kinetics are going to function on. Not the air temperature, but the temperature of the grain itself. So grain, moisture, and temperature combinations, if I can control the temperature of the grain when it's wet, and I can also control it when it's dry, I can get all sorts of different specialty malts out of it. And we're going to go into all of that later as well. So let's start out with a review of psychrometrics, okay? Now, for me, the easiest thing to visualize, because this happens to everybody, is I'm bathing. I'm taking a shower in the morning. Okay, I'm in my bathroom. I have the door closed and I have the fan on and I'm taking a shower. So the shower is finished, and then I rip open the curtain, and all of a sudden I get cold, just like this guy is doing. He's shaking, he's freezing, he's cold. And why is he cold? Well, he's cold because of wet bulb temperature. Okay? So he's not feeling the air temperature, he's feeling the air's wet bulb temperature. And why is that? That's because there is moisture on the surface of his skin that is evaporating. And that evaporation, and it's evaporating because the air is picking up the moisture. That evaporation requires energy. All right? It takes a lot of energy to evaporate liquid water to make it vapor. And that energy is all coming out of your skin. Okay? So anyway, My bathroom is heated to 68 degrees Fahrenheit, okay? And if I'm in the dead of winter, so here's the cool thing, and it defines what I'm trying to explain. In the wintertime, I feel 38 degrees Fahrenheit. And in the summertime, at the same temperature of the bathroom, I feel 68 degrees Fahrenheit. So I'm feeling 30 degrees difference. Myself, I feel 30 degrees difference in temperature simply due to the outside air condition being the dead of winter or the dead of summer. 30 degrees, right? And that's with my bathroom being heated at 68 degrees Fahrenheit. So if I think about me being me being a grain of malt sitting in a pile of other grains of malt, and air gets hit to me, the same exact thing happens. The grain doesn't experience the air temperature. The grain experiences the wet bulb temperature, or something in between the dry bulb temperature and the wet bulb temperature, depending on how much water is evaporating. All right, we'll get into this more later. So the beauty of psychrometrics is that if I know any two thermodynamic properties of air, if I know any two of them, then I know all the other ones. If I can get two thermodynamic properties, it defines everything else. Okay? So the easiest way to measure both these thermodynamic properties is using a wet bulb and dry bulb thermometer. So we all know dry bulb thermometer, and we know that a wet bulb thermometer is really a dry bulb thermometer that's got a wick on it, and the wick is constantly saturated with water. Okay, so as basically, if the air is dry, then the water evaporates off that wick, and that drives the temperature down, and that is your wet bulb temperature. Okay. A hygrometer is basically something that measures dry bulb and wet bulb temperature. If dry bulb thermometers are real easy to use. All right. If you need something to measure the second property, wet bulb temperature is usually the easiest and most repeatable way to do that, because it's mechanical and it's simple mechanical. A wet wick, a saturated wet wick. I've had lots of experiences with electronic hygrometers and electronic relative humidity sensors, and they're very expensive and they do not survive kilning, and they give poor information. So my recommendation to you, if you're out to learn a second psychrometric property of your air, utilize a wet bulb thermometer in as many cases as you can, and then possibly use what you know about psychrometrics to extrapolate other properties off of that. And I can try to show you what I mean by that. So a psychrometric chart is nothing more than a graphical representation of all these thermodynamic properties. And who uses these? Heating and cooling engineers, refrigeration engineers, anybody that is in design of processes involving the addition of energy or moisture to air, or the elimination of energy and moisture from air. That's who uses these. And hopefully maltsters who are trying to develop the perfect malt. So here is a psychrometric chart. All right, we'll take a little bit of time here because I want you to see how this thing works. Okay, so on the x-axis here is your dry bulb temperature. The y-axis is the humidity ratio, or otherwise known as absolute humidity. So constant absolute humidity lines are these horizontal lines. Okay. These lines here are the constant air density lines. Energy for constant enthalpy, The energy of your air, the constant enthalpy lines are these lines right here. Okay? And finally, we have these curved lines that are the constant relative humidity lines. And so it's pretty simple. If you pick one point on that, which would be defined by any two of those values, then you can read all of the other thermodynamic values from that. Okay, if any two of my thermodynamic properties are known, I will find a point on that graph and I can read all of the other properties from it. Or I can, be much more vigilant and get even better numbers by using an online psychrometric calculator. This one is the one I like. It's from Sugar Engineers. You basically would pick 2 points. You tell it, you have to give it a dry bulb temperature, and you would tell it that you want either to tell it wet bulb, relative humidity, or dew point. And after entering those two values in, all the other values pop up for you. Okay, this makes it really super easy. Trying to read numbers off that psychrometric chart, although quite possible, is very time intensive and irritating. So let's talk about this one, this first unit operation here, which is air heating. It's a pure air heating operation, meaning I'm only adding energy. I am not adding or taking out any moisture or air. It's only an energy addition. Okay? So what I'm doing is I'm taking air, I'm adding energy to it to raise its temperature to whatever my set point is. Okay? Because I'm a chemical engineer, I have to show you mass and energy balances. You do need to use these to make those numbers that you're getting off your chart mean anything. But in this case, I have an input air that is a mixture of air and water vapor. I have an output that's a mixture of air and water vapor, and I'm also inputting energy. So for material balances, my air and my water vapor material balances tell me that I've got the same amount of air coming in and the same amount of water coming in as I have going out. My energy balance, though, tells me that I am adding energy to the input air energy to create a higher energy in the output air. Okay? That's that simple. That's it. I kind of wanted to show you an example of how you would see this on a psychrometric chart. All right, so I'm going to give us a very simple example. Outside air today is at 80 degrees Fahrenheit and 70% relative humidity. All right, I want to heat that to 140 degrees Fahrenheit and put that on my kiln. So first question would be, what are the physical properties of the 140 degree air that I'm applying to the malt bed? And how much energy should my heater be consuming in this heating operation at this point in time? So we get out our handy dandy psychrometric chart, and we know that our outside air is at 80 degrees Fahrenheit and 70% relative humidity. Okay? So 80 degrees Fahrenheit is this line, constant 80 degrees Fahrenheit line right there. And relative humidity is 90, 80, 70% relative humidity is that curvy line right there. So that point is our input air into our heater. Okay? As I add energy, I am not adding any moisture, so my absolute humidity does not change. These horizontal lines are the constant absolute humidity line. So I already know that I'm going to go from here somewhere over here on that line when I'm heating air. Okay? Well, I've got a set point of 140 degrees, so I got to stop there. That's my point, 140 degrees. And now I've got new output air. My output air is at 140 degrees, but now relative humidity has dropped down to 13%. Then all of the other physical properties. All right, I know how much moisture is in the air. I know how much energy is in the air. I know what the wet bulb temperature is. And I know what the specific volume of the air is. I know what its density is. I know all of that stuff, okay? I know how much energy is in it, what its density is, what its moisture content is. Boom. Just like that. So pure energy addition process is always going to look like this. Every time you see one, it's going to look like this on the psychrometric chart. A horizontal line to the temperature of desire. All right? That's it. So, the answer to the first question of the physical properties of the 140 degree air that is being applied to the kiln, here they are, 140 degrees Fahrenheit, 13% relative humidity, all those numbers, okay? How much energy should my heater be providing in this heating operation today? Okay, well, I've got all the information I need to calculate that, okay? Energy that I'm adding to my kiln is the output air energy minus the input air energy. Can't be much simpler than that. And I already know what those energies are because I found them on the psychrometric chart, okay? This is the mass flow of air times the absolute humidity out minus the absolute humidity in. And the mass flow of air is the volumetric flow rate of the air divided by the specific volume of the air. That comes off the psychrometric chart. In the end, right, my equation comes down to the energy I'm adding to the kiln to do this is whatever my volumetric airflow is times 0.97 BTUs per foot cubed. So let's say if my airflow was 1 foot cubed per minute, then my energy requirement would be 0.97 BTUs per minute. All right? For each cubic foot of air pulled through the heater, 0.97 BTUs. Well, I can't even read that. 0.97 BTUs are, for each cubic foot of air I'm pulling through the heater, I am using 0.987 BTUs, okay? There's a lot of stuff you could calculate at this point off of this, a lot of different things, but that's just one example. If I'm looking at now malt bed drying, so now I'm running hot air through a malt bed, this becomes an adiabatic saturation condition. What that means is that I am not adding any energy or taking any energy out, but I am adding moisture to the air, and that's coming off of the moisture that's in the malt. Okay? So if you think of the malt bed with a bunch of individual grains acting as individual water vaporizing wicks, just like a wet bulb thermometer, okay? I can model that as an input of the grain drying rate into my input airflow to get output. So what this is, adiabatic means constant energy. So this is a unit operation that adds moisture to the air at constant energy. All right, and that's what these mass and energy balances are telling you, right? My energy is constant because my input and my output energy are the same, but I'm adding grain drying rate to my input vapor to get output vapor. So this is a pure water addition process with no change in energy. And what that means then is we follow the adiabatic saturation line or the constant enthalpy line. Okay? So I'm running air through a bunch of wicks that are giving me water. So it's increasing the relative humidity, which is in this direction. And it's doing it without any energy addition. So the energy here is the same as the energy here. This is what all adiabatic saturation processes look like on a psychrometric chart. Okay? This would be my exhaust. This would be, I don't know how far up here I am because I don't know what the drying rate is. All right? But guess what? We have the rate of drying curve for our malt, and we will know what the drying rate is at the different moisture contents. But if I'm above the critical moisture content, my drying rate is maximized and constant. I have a constant drying rate. So in the constant drying range, and I'm telling you right now that's above 25% malt moisture, I don't know that to be true, but from what I've seen, what I've experienced, that's roughly what I think it is. Anyway, uh, the drying rate, when I'm above 25% moisture, the drying rate of my malt is always sufficiently high that my kiln exhaust is going to leave at 100% relative humidity. What I'm saying is that I can't put enough air on that malt to reach that maximum drying rate. If I find that I don't have saturated exhaust, if I find that my humidity isn't 100% by measurement in the kiln during the constant drying range, when I'm above 25% moisture, then I probably have a problem. I probably need to go find out where there's a hole with air bypassing the kiln. Okay? Nothing more than a waste of energy. Anyway, when I'm in the constant drying range, drying at 100%, drying to saturated exhaust, the entire grain bed is going to approach the wet bulb temperature of the drying air. You can see, if you wanted to model this, you can see that if you were kind of model a grain kernel, and there would be there's an interface between the air and the kernel where there's water being converted to vapor, and right at that interface you're at 100% humidity. It has to be. And if you're at 100% humidity, you have to be at the wet bulb temperature. Your dry bulb temperature and your wet bulb temperature have to be the same. It's a must. Okay? So physically, your grain bed is going to want to become the wet bulb temperature of the drying air, and that will also be the exhaust temperature. Your exhaust air temperature as well. Okay? And this is true for air capacities of at least 55 CFM per bushel. And it's true for higher air capacities as well, until you get to the point when you are fluidizing your bed or blowing your bed out, or in other ways creating a bypass condition where the air is not flowing through your bed but is flowing around it. All right. So back to this. If I'm starting my kiln up, I'm definitely in the constant rate period, the constant drying rate period. So I know now that my air is leaving the malt bed at 100% relative humidity. So that gives me the other point. I'm somewhere on this line at 100% relative humidity. This is where my exhaust is. All right. So I have an exhaust temperature of about 87 degrees at 100% humidity. But I've also gained a bunch of moisture. I'm up to 193 grains per pound of bone dry air, where before I was only at 108 grains per pound of bone dry air. Well, the difference between those grains per pound of bone dry air, that's my drying rate, okay? So my drying rate is 193 minus 198 grains per pound of bone dry air. Oh, and somebody's going to ask, what is a grain? A grain is a unit of mass. It is 1/7,000th of a pound. You use grains so that you don't have to use lots of decimal points and zeros you have to use lots of decimal points and zeros to describe humidity of air, absolute humidity of air in pounds per pound. So you describe it in grains per pound just to make the numbers easier to look at, quite frankly. So back to our example then, to determine the drying rate, we simply subtract the moisture content in the output from the moisture of the input, and that gives us an answer of volumetric airflow times 5.5 grains per cubic foot. What that means is for each cubic foot of air pulled through the bed, 5.5 grains of moisture are removed from the bed, and that is happening during the constant drying phase. So now I can go back also now and use Psychrometrics now to find out what's happening when my outside air temperature changes on me. Okay, so this is like the summer versus winter kilning question. All right. So if I've got outside air at different combinations of outside air temperature, 0 and 80, and outside air relative humidity, 5 and 100, these are the wet bulb temperatures that the bed is going to try to achieve through all of that. If I'm looking at the dead of winter here, I have 70.8 degree Fahrenheit bed temperature, and in the dead of summer with 80 degrees and 100% relative humidity, I've got 93 degrees Fahrenheit. Since this is all happening during the constant drying rate period, which is before breakthrough, and breakthrough happens at about roughly 10 hours. Let's say it's 10 hours. In the wintertime, I've got a malt bed sitting for 10 hours at 71 degrees, and in the summer, I've got a malt bed sitting for 10 hours at 93 degrees. That 10 hours at that 93 degrees temperature is enough to create precursors and give you a darker color malt. Why do we get darker malt in the summer versus the winter? That is one of the reasons why. The higher energy outside air, the higher humidity outside air, creates higher wet bulb temperatures during the constant rate period. All right. If I wanted to know the drying rate as a function of outside air temperature and humidity, I'm showing also that in the summertime, the drying rate drops, is dramatically reduced from what it was in the wintertime. So, basically what happens in the summertime, my bed temperature increases, which gives me more precursors for color formation, and my drying rates fall, which keeps me into that higher temperature zone with precursor formation for a much longer time, because it's all happening before the malt gets dry. Okay, so that kind of answers summer versus winter, and it's all just due to the energy of the outside air and the absolute humidity, higher absolute humidity creating higher wet bulb temperatures at saturation. Okay, now let's get into some specialty malts. What are specialty malts for me? Specialty malts and base malts, I don't see really a difference. They're all malts. They all require something unique, and for me, a specialty malt is just a combination, a specific combination of barley variety, malt modification level in germination, how much active enzyme is left over in the completed malt, how much enzyme action is going on during kilning, because enzyme action during kilning creates the precursors for the color formation, and then the color and flavor and finished malt. So what I'm saying is that specialty malts are really just different combinations of those things. All right, and as an example, I just showed you what I felt were like different specialty malts I can make on kiln, rated for enzyme activity and then also rated for color and flavor. And you can see that I'm getting all sorts of combinations of just enzyme activity and flavor and color, all right, to define these different malts. So if I added 3 more descriptors in there, you could see that it'd be very complicated. But basically, a specialty malt is just a unique malt that people want for whatever reason. Specialty malts are produced on kiln by controlling combinations of temperature and moisture, and this is especially critical when the moisture content is really high. Okay, because we can use this to select which enzymes are active. We can use these combinations to select which enzymes we deactivate. We can also use these combinations to control color formation and flavor formation. I wanted to say something about optimal enzyme activity. So while you're kilning, right, you're at a lower temperature, you're at a fairly low temperature, and you're getting the Michaelis-Menten kinetics for enzyme catalyzed production from a substrate. All right, so this is what's happening on this side of this curve. This is showing you the rate of an enzyme catalyzed reaction versus the temperature. And I just wanted to make the point, I didn't know everybody realized that the reason that it starts high and goes down is because you really got 2 competing reactions going on here. The first reaction that's happening, that's dominating on this side, is simply the enzyme catalyzing the formation of product. On this side, the enzyme itself is becoming deactivated. All right, because of increases in temperature. And you can actually model the Arrhenius temperature dependence on the deactivation and on all of these rate constants using Arrhenius, which is a logarithmic type approach. Again, the correct temperature in these kinetics is the grain temperature, not the applied air temperature, and it's going to be way different, okay? These reactions also need moisture, so these are all happening higher at higher moisture contents. Enzyme deactivation, for example, we know that enzymes deactivate, they get they're much more sensitive at high moisture, and they become much more stable at low moisture. There's also the fact that these enzymes are kind of locked in a matrix inside the barley, and that helps stabilize them and well. So you're not going to see the same exact stability as you would see in glass, okay, in the test tube. So anyway, just wanted to explain that one. There's a lot of different enzymes that are that we can activate. If you're looking what we believe the pH of the inside of the kernel to be, we can see there's all sorts of enzyme systems that can be activated while the grain is still wet. So if I can take high moisture malt, I can optimize the malt temperature using psychrometrics. I can hit a malt temperature that optimizes, for example, proteolytic activity. All right, so you just find some proteolytic activity, find out what temperature you need it to be, and activate it. And also carbohydrates activity. All right. Now these are all happening very slowly below their optimal temperatures. So a long period of time at slow reaction still gives you some results. So anyway. You can get, basically though, utilizing select temperatures just during the before breakthrough phase of kilning, you can control, you can get activity from a little bit of activity from a lot of these enzymes, and then by increasing that, you can actually select out activity of other enzymes and deactivate other enzymes. Okay. While you're doing this, you're also producing the precursors to color formation. So your precursor levels go up, which means color is easier to form as your precursor level goes up. In traditional kilning, these are the biochemical changes that I was talking about before. All right, when the grain is wet, you can increase the wet grain temperature, you can increase protease activity and carbohydrates activity and other enzyme activity as well. That gives you the Maillard precursors. All right, if you got too slow airflow, then you can actually get some microaerophilic lactobacillus growth, and that will give you color as well and flavor as well. So don't discard that as a don't discard low airflows as a proper tool in specialty malt formulation. I would suspect a lot of the melanoidin malts are produced that way. And you got to worry about sour, musty off flavors. All right. I hear this a lot. I'm hearing this a lot lately. Protein is flavor. I don't think so. Look, we all know the Maillard reaction, right? It's basically condensation between free amino groups and reducing sugar. So you need protein and you need sugar, right? So protein is not flavor. Protein is a part of flavor. That's the best I can say about that. Okay. Also, it's really important to point out that these are free amino groups that we are reacting. All right. Big proteins don't only have one free amino group. So free amino groups aren't proteins, they're chopped up proteins. Okay. So a higher total protein is not giving you anything. All right. Okay, I'm finished because I'm out of time. Thank you all for your attention. I really hope that this may have sparked some interest, and that you see the power of using psychrometry. You know, you can basically do on paper everything before you even try to make malt, and it will be freaking close to right off the bat. Okay. Anyway, thank you very much for your time and your patience and your understanding, and have a great day.